The following presentation covers the data preparation and statistical methods for creating the snow climate analysis tools. It's being prepared as part of the BCIT GIS 8150 final project. Part 1 of this presentation covers the sources of data used in this project. This project uses maximum annual height of snow data, and the project area is limited to British Columbia. The data is obtained from a variety of sources which are explained in subsequent slides. The chart at the bottom shows a typical time series with each spike in the data representing 1 year. It's worth pointing out that we use winter year rather than calendar year with this data, and that means that any data that's recorded in December is included as part of the following year. You could also think of it as being split down the middle through the middle of the summer. That's the break. So what we're recording is the spikes at the top of each of these, so that each year is represented by a single number in centimeters. If you were doing this in Excel, you would use the following formula. The first type of data is manual snow height data. This is typically recorded once or twice daily by an observer. It is observed by reading an interval off of a fixed snow stake, as shown in these pictures. You can see here an example of a snow stake, and here. And both of these have 1 centimeter intervals, and it's often every 10 centimeters is denoted by a bolder line, so it's easy to distinguish. The responsibility of the observer is to clear the snow around the stake or fill in any holes such that the value being readed off the stake is representative of the surface surrounding the stake, the snow surface. This is highly reliable data with properly trained people. The second data type is automated snow height data, which is captured using a downward-facing sensor at an automated telemetry site. In this case, we have 2 examples. These are common adjacent to highways and snow pillows and other places where data is being captured automatically. The problem with this type of data is it often contains errors, so it requires a human to filter it prior to using it. In the example here, there's 2 artificial spikes in the data which are circled in red. These had to be removed before the maximum values from all the rest of the years could be properly assessed. This all adds time to the processing. The third type of data used in this project is snow course data. This is collected manually using a hollow coring tube, which is inserted into the snowpack all the way to the ground. By obtaining a sample of snow, it can be weighed, and knowing the volume of snow and the weight of snow, we can convert it to a liquid water equivalent or snow water equivalent, which is used for hydrology. This is highly reliable data, but the problem with it is it's only observed once per month through the winter. So we're not capturing a true maximum height of snow. However, this data set goes back to the 30s. It's often in high mountainous areas where other types of snow data are unavailable. So it's not the best data for observing max HS. It's still very useful and interesting. These photos are decades old, but the methods haven't changed at all. So this project uses 5 data sources. BC Ministry of Transportation and Infrastructure has 2 data sets. They have a modern electronic data set from their automated telemetry, and they also have a historic manual data set. Where this data set of manual observations is in exactly the same location as the modern telemetry, they were combined to create a much longer data set. So that's the BC MOTI combined data set. Often these are spanning several decades, whereas the electronic data typically only goes back to the early 2000s. Parks Canada in Rogers Pass has a robust data set at the highway elevation and up at tree line elevation, and these are collected manually going back about 60 years. It's very high quality data. And then Environment Canada is similar to the BC and MOTI combined, where historic observations were typically collected manually and modern observations are collected using telemetry. So they were combined where they were located in the same spot. And then finally, the BC River Forecast Center is just manual snow course data. The second part of this presentation covers the statistical methods used for normalizing the annual data. The first method is to calculate the annual percentage of average. This is used commonly in hydrology, and you may have seen figures like the one on the right, which shows the snow basin water index. These maps use the snow water equivalent, which is a measurement in millimeters, whereas our project is focused on height of snow in centimeters. The basic formula here is to take an annual value, subtract the average of the data set, and then divide by the average of the data set. And we add this number to 1 to create a value where 100% value equals the average. Anything less than 100% is below average, and anything above 100% is above average. So if you want to pause this slide, you can read through the examples, but we're showing one example where the value is below average and results in a 70%, and the other example is above average and results in 120%. The other videos cover the use of these dashboards, but this is what the annual percent of average data looks like when it's plotted. Each of these circles represents one station, and the number inside of the circle is the actual value for that year. So here we see a station with 145%, which is 45% above the average. Some of these much smaller orange ones are well below average. The second statistical method is more complicated, and the next few slides are going to go into the weeds a bit on extreme value statistics. This method, we are using the extreme value type 1 distribution, which is also known as a Gumbel distribution, and we're using the maximum case. So this is a probability function, probability density function shown on the right here, and we can see on the minimum side it goes to 0. That means we're not expecting extreme events on the low side, but on the high side we see this tail extend out. So basically what this means is for maximum height of snow, our extreme events are when we have a very deep snowpack. Below is shown the Rogers Pass data set, with each year being represented by a bar. Based on this data, we can calculate the average, which is shown here in solid black, and the standard deviation. And it's pretty common with extreme value statistics that we would say an event is considered significant if it's outside of 2 standard deviations, which is shown as the second line with the smaller dashing. So in this case for Rogers Pass, we see one event which is beyond 2 standard deviations. The main statistical methods used for this analysis are taken from Dr. Bruce Jamison's book, Planning Methods for Assessing and Mitigating Snow Avalanche Risk, Chapter 6, Methods for Applying Snow Climate Data. We're using a non-exceedance probability, which is equal to 1 minus 1 over t, where t is the return period in years. To determine the extreme value for any given return period t, we use this formula here, where x over t is the event, and u and b are scale parameters. In Dr. Jamison's book, he uses a fitting method to determine the scale parameters u and b. This method likely estimates the return period more accurately than the methods used in this project. However, it's more labor intensive estimating U and B. So the second half of this slide covers a more generic method called the method of moments, which is taken from a statistics textbook. Basically, what the methods of moments means is you're assuming a set of sample data is representative of your population. And we're assuming our population fits the probability density function shown on the previous slide. So basically, if we're assuming our sample data fits our population, we get the following two formulas where mean equals U plus Euler's number times B, and the standard deviation equals B times pi over the square root of 6. If we rearrange both of these formulas, we get the two formulas here at the bottom where B equals the standard deviation times the square root of 6 over pi. That's one of our scale parameters. And U equals the sample mean minus Euler's number times B. Or the sample mean can be rearranged. Instead of using B, you can use the standard deviation. So basically, we get these two formulas, which are functions of our mean, our sample mean, and our sample standard deviation. And then we calculate our scale factors. So back to our Rogers-Pass example. The sample mean in this data set is equal to 199 centimeters, and the standard deviation is equal to 34 centimeters. So once we know those two numbers, we can calculate B, which is equal to 26, and U, which is equal to 184. Now that we know B and U, we want to calculate the 10, 30, and 100 year maximum height of snow values for Rogers Pass. To do that, we create a table shown on the bottom left-hand corner here, where first we calculate the probability for each of the return periods. Then we can calculate the negative natural log of the probability, and we use that plus our formula here to calculate the 10, 30, and 100 year values. These values can then be plotted over the existing chart here to see where each of our years falls. So in the case of 1972, we see our values above the 100 year height of snow. And 1967 falls between the 10 year and the 30 year. The data on the previous slide is useful for producing summary values for each station. What we can also do is flip these formulas around, and we can calculate the estimated return period for each year in the data set, as shown in the table and on the chart. So the formula here, the first formula is the one we already used. So we flip that around and we solve for P, and then we sub P into our formula to calculate T. So this ends up being the formula that goes into this field in our table. And going back to 1972, we see we end up with a 174 year value of return period. And in 1967, as we said, it falls between the 10 and the 30. We ended up with 21 years. So these labels on this chart represent the individual values. Typically, anything below the mean is a 1 or a 2 year type of return period. And then finally, this estimated return period data can be plotted. I won't cover how the dashboard works, that's in the other video, but this is basically a distribution of 1972. As mentioned before, Rogers Pass saw 174 year estimated return period. We see a number of stations showing significant events in 1972 throughout southern BC. Now that we know the sources of data and the statistical methods used, the final part of this presentation covers how we actually create the project data files. This flowchart shows the basic structure of how the data is created. There's two main data tables. There's the station HS data and there's the annual HS data. These are comma separated table files. The first step is to populate these tables with metadata from the various sources, and on this side we're populating the annual maximum HS values. As a result, the annual HS data CSV is much larger than the station HSV data. The second part, once we have all the annual data into a table, we calculate summary statistics as number 2 and populate the rest of the HS station data. Once the HS station data is populated, we use those values to normalize the annual values in the annual table. So we'll cover the rest of how this works in subsequent slides. So this is what the tables look like at the initial step where we've populated the tables. The station HS data has one row for each station, and the basic metadata is taken from the source data. And the annual data at its bare bones just has a station ID, the winter year, and the maximum HS value for each of those years in the data set. Once we have the annual data in a table, we would select that data, all of that data, and insert a pivot table. The pivot table can be used to calculate all of the summary statistics all at once with a limited amount of effort. So the basic pivot table fields entry is shown here, where we have 7 fields entered down here, and each row is represented here by a station ID. So you can see we have the average of max HS, the standard deviation, the count, the max and min of HS, and then we also have the max and min winter year of the data set. Once you run this pivot table, you get the example here at the bottom where each station has an average, standard deviation, count, and so on. And this data can then be brought back into the station data table. This is what the station table looks like once it's complete. So we have our original metadata, A to G. Then we have our 7 fields here, which are calculated from the pivot table. Once we have those calculated, we now know the mean and the standard deviation, and we use those values to calculate B and U here, and B and U are then used to calculate the following 3 10, 30, and 100-year values for each station. So this is a look here at the station HS data table when it's complete, although all the stations aren't showing. And the formulas are included at the bottom. Once the station HS data table is complete, we can then use Lookup Functions to calculate the normalized annual values in the annual HS table. Basically, a lookup function is used to find, based on a single value, it'll look up an array and then it will return the value in a corresponding array. So at its very basic, it has 3 values. It has its lookup value, the lookup array, and the return array. What this replaces is HLOOKUP and VLOOKUP, which were a little bit clunky in the past. This is a much easier formula to use, and it works both vertically and horizontally with a single formula. Basically, in this formula, we're calculating the annual percentage of average, which has been described in previous slides. And in this case, K2 is equal to the max HS for any given year. And then we're looking up for the given station ID. It's looking in this green range to find the ID. And once it finds that station ID, it's going to return the value from this array. which in this case is the average value. So basically, once we create this formula once, we can use it to calculate the annual percentage of average for every single year at every single station in the data set at once. This is the formula for annual estimated return period, which we saw before. We use the same style of XLOOKUP to find the values of U and the values of B for each station to calculate the estimated return period for the given year's max HS, which is K2. The XLOOKUP function can also be used to carry metadata forward from the station HS table into the annual HS table. In this case, I've carried forward the name, elevation, station type, station status, the lat/long coordinates, the average HS of the station, and the number of years in the data set. The reason for doing this, well, this data is captured in the station table. I wanted to include it in the annual table in order to properly populate the pop-up windows in the maps I've created. I wanted some of this data to be available, and this was the easiest way to do it. So this is what the final annual HS data table looks like. You have A through I, which is all station metadata. And then you have the 2 rows, which is the annual data, with each year having corresponding max HS value in centimeters. And then you have the 2 fields which were discussed, which is the normalized annual data, which is the estimated return period and the percentage of average for each year. The final slide shows the Arcgis online data structure used for this project. As discussed, there are 2 main tables which are used as input data, the station HS data and the annual HS data. We also use 2 sets of polygons, one representing the River Forecast Center's snow basins and the other representing Avalanche Canada's forecast regions. This input data is used to create feature layers, which are hosted on Arcgis online. The 4 feature layers are used to create the web maps and dashboards, as well as the Arcgis Insights pages. These dashboards and pages are used to create the final web mapping application, and they're also included as part of the story map tutorial, which you're currently watching.